we will discuss about the formation of stationary waves in stretched strings. So we will call that also as vibrating strings. So already I have shown you that the distance of a node from origin, which is equal to n times lambda by 2, that is in terms of wavelength. So the distance of a nodal point from the starting point is given as n lambda by 2. This is what we derived earlier. So if the length of the string is taken as n, since the string is attached at the both ends, then we can say that n lambda by 2. This is if L is the length of the string. So from one end to another end, the other end is also connected to the rigid boundary. So that also will be a nodal point. Therefore, L is equal to n lambda by 2. Suppose if I consider n is equal to 1. If you take n is equal to 0, it means it is the first fixed point from which the waves are being considered. So for n is equal to 1, what we get is L is equal to lambda by 2, or lambda is equal to 2n. If you want to derive a formula for the frequency of oscillation, then you can make use of the same thing from this. From L is equal to n lambda by 2, and lambda is given by 2L by n. So from our formula for the wave velocity, V is equal to nu lambda is already shown to you. So from which nu is written as velocity of the wave by wavelength. So therefore in general, in this case you can write like this: nu is equal to V by 2L, and then n goes to the numerator. So for n is equal to 1, u1 will be equal to V by 2L. So that means the length of the string, if that is equal to half the wavelength, you know that distance between two successive nodes is lambda by 2. That can be shown from this formula. And if it is vibrating in the first mode, that is in the least value of n, that is n is equal to 1 we have taken. In such case, the frequency formula we got is V by 2n. And this frequency with which the string vibrates, then we call that as fundamental mode. Fundamental. This is also known as first harmonic. First harmonic. And suppose if you take n is equal to 2, so from this formula you will be getting the frequency equation 2 times V by 2L. In this case, you will have two loops formed like this. So that is, here this L is equal to lambda by 2. In this case, the total length will be equal to lambda. In such case, the frequency of oscillation of the string is said to be second mode. This is second mode of vibration, or we call it as second harmonic. So which is 2 times to the frequency of the fundamental mode. And you can see from this formula, the second mode of frequency is 2 times the fundamental frequency. Suppose this n is taken as 3. Then we can easily say that the string will be vibrating with 3 loops. That means in such case, the total length of the string in terms of wavelength will be equal to 3 times lambda by 2. That can be obtained from this formula. So the frequency formula will be nu3 will be equal to 3 times V by 2L. So that is nothing but 3 times mu 1. Now you observe this formulas, that is 1, this is 2, and this is 3. Now you observe the formulas we derived 1, 2, 3. Like that you can continue. What we get is the relation between the fundamental frequency and higher harmonics is 1:2:3, etc. So that means if a string is stretched between two rigid points and if it is plucked, then it can vibrate with different harmonics. So it will have both even harmonics and odd harmonics. Harmonic is nothing but the multiple of fundamental frequency. Now a string, when it is excited, can vibrate with several modes, but only some modes are more intense, will have more intensity than the others. So strings when vibrated can vibrate with certain modes predominantly than the others. For example, when you observe a musician playing a guitar or any string musical instrument, he will be producing different sounds by striking or plucking or bowing the string at different points. He will be pressing at some point and he will be vibrating the string. So if you change the positions of pressing the string, the sound quality changes. So it means we can vibrate the string with several modes, but out of them only some are more pronounced, more intense than the others. Okay. We have seen that a string can vibrate in different modes, and we derive the formulas for frequency of vibration of different modes of a stretched string when standard waves are formed. So when the string is vibrated, it will make vibrations in such a way that the waves produced are transverse waves. So we can discuss some laws regarding the transverse vibrations of stretched strings. So we know for fundamental frequency of vibration, the formula you got is mu is equal, that is mu 1 is equal to V by 2L, where V is the transverse wave velocity in the string, L is the length of the string.